review what we talk about the rounded errors and the shopping and the significant figures. And we said these usually errors due to our representation or to the machine representation of the numbers. If we have any calculations, so the machines by itself doing some approximation based on the instruction that we enter in our algorithms. So this might give some approximation to the number. As we said, we take an example for the pi, for example, machines may approximate the number of digits in the pi, for example, from we have, for example, 8 significant figures to reduce it, for example, to 4 or to 5 significant figures. This difference in the representation of the numbers we represented by rounding errors or rounding off errors, because sometimes we approximate. If we approximate, sometimes the approximation will be greater than the true value. If we do rounding, if we do shopping, in this case, the true value will be greater than the approximation. So in this case, otherwise we have we increase the value or decrease the value, and this will cause some change, for example, in the value, and this will cause errors. And because we usually use absolute value of the error, so in this case, otherwise the error is negative or positive, this will not affect because we focus on the magnitude and how far we from the real value or how far from the true value we are. Also, we give some examples about the shopping and the rounding, and we said rounding, we just replace the numbers by the nearest number. Usually, if the number, if we are interested here, for example, for two significant figures, or for example here, so we put a line here or cutoff point. After that, we look for the number after this cutoff point. If it is greater than or equal 5, so we do rounding. That means I will increase the number before the cutoff point by 1. Shopping, this is different. In this case, if I am interested here in the number of significant figures, for example, if we are interested in, for example, 2 significant figures. So in this case, I will make a cutoff point after 2 significant figures. The first one is 1 and 1. After that, I will create a cutoff point here. I will look at here, no way, for example, to look to the number after the cutoff point. We just throw all the numbers after the cutoff point, and we call this shopping. And we take different examples. I think if you go through the this website and these examples, you will be in good shape, inshallah, in the exam, because usually in the exam we give you some calculation, but the final answer we need it in some forms. Okay, so this is very important to get the complete or the full marks in the exam. Also, we have rules for the significant figures. We said any non-zero digits, we call this as we consider this as a significant figure. Zeros between non-zeros. If we have 0 between 2 non-zeros, so the 0 here will be significant. Leading zeros always non-significant. If we have zeros leading, so these zeros are always non-significant. Trial zeros that comes at the end or at the right, it is sometimes significant and sometimes not significant. This depended on the presence of the decimal point. If we have decimal point, so the trial like this one, this will be significant figure. Also here, for example, if we have decimal point, so the trial or the zeros that comes at the right will be significant. Without decimal point, so this trial just to fill the place, and it's not a significant figure. I think we do some of this one. We stop it here, yeah? Last lecture, Shabab. At this point, yeah?
Yes, we stop.
Yes.
Yeah, we stop. Yeah, we'll stop it here. Okay, so here what we have, sometimes here we do, this is examples, so just look for these examples. I think if you are, because here we have some students, they are just attend more than 5 or 3 or 4 students, they just join us. And today is the last day until 12. After that, no more, yani. The student will come to this class. Okay, so here, for example, we have, as we talk, for example, about the examples here. For example, this, let's review this example. After that, we'll go to another topic, for example, for adding and multiplication of the significant figures. So here, for example, if we have this number, and the question is to round this answer, for example, to 4 significant figure. Okay, we said any number non-zero is significant figure, so we have here, this is significant, this is significant, and this is significant, and this is significant. So in this case, we create a line here after these four places. This is the first one, second, the third, and the fourth, and we create a line here. After that, we look to this number. If this number is greater than or equal, greater than or this is greater than or equal 5, so in this case we'll do some increment by 1 to the number before the cutoff point. If it is less than 5, so in this case we'll keep the result like this one and we throw this out. So in this one, because this we have 5 here, so we just do increment here to the 7. So 7 now becomes 8, and after that I will throw the 5 out. Okay, so the same thing is here. As we said, the same thing is here, but here what the problem, because sometimes and some books they focus on one point, that I had this example here. If you look here, if this number is odd, so we do the increment. If this number, if the number is 5 only, okay, not 6. If 6, so we do increment. If this is 7 now, and this number is odd, okay, so in this case we add 1 to make this even. And in the other case, for example, if you look for this example, we're looking for 4 significant figures, so we create a significant figure here, and now this number now after the cutoff point is 5. If you want to do increment, if this number is already even, okay, sometimes we leave it alone, no change, we just throw this out. Okay, this because to avoid the remainder in our results, because usually all the numbers or binary number we use it are based on 2 or 2 base. Okay, otherwise 2 power 0, 2 power 1, like this one. So if it is even, so we keep it even. If it is odd, we do increment. Okay, and for some books they do increment for all the cases. Okay, it's so dependent from what science they use, otherwise computer based or chemical or control guys, is dependent on what science we usually do. Okay, شباب. Just the things that we want to review, I added here some examples, and these things I will put it inshallah in the homework. Okay, I give it from now. You will have it inshallah in the homework as exercise to do. Okay, شباب. Okay, that's it. Here usually if we do additional adding or subtracting numbers for different decimal places, so usually the answer is equal the least number of decimal places. So your calculator should present the answer in this formula at the minimum decimal places from the numbers. Okay. We talk here about decimal places. Okay, so here for example we have these examples. I have this number contain 3 decimal places. You can see this is 3 decimal places here, and the second number we have only a single decimal place. So the result is equal 46.118. So the final result should be approximated to a single decimal place. So the answer or the representation of the answer should equal, if we have subtracted or added, or contain the number of the decimal equal the minimum of decimal place that's contained and the number that we added or subtracted. Here, for example, the other things here we have this example. We have the first number, we have 4 decimal places, and here we have 3, and this is 2. We have 5 decimal places. Okay, so in this case, how many decimal places we have? The answer we have here 5 decimal places. What we should do, the machine should approximate the answer to 4 decimal places. Okay, so it approximate the answer to the minimum result. Okay, how many decimal places that we have it? The minimum number, we put it here. For multiplication and division, and usually we talk about how many or the number of significant figure, not the decimal places. We talk about the significant figures. Okay, and we know the definition of the significant figure, how many significant figure that we have. Okay, so here we talk about the significant figure, and this significant, as we know, and these two are significant. We have 3, and this is 0 between, so we have here 5 significant figure. And this one, you can look for this one. We have how many significant figure? We have only 2. Okay, we have only 2 significant figure, and the result here is comes with 3 number. The result that we have, we should approximate these to 4 or 2 significant figure. Okay, 2 significant figure here, and because this is already this one, it should be have here 4 or approximate this to 4, because sometimes, because this is even, you can see sometimes we not use because the resources are not fixed. Okay, and this because is even, sometimes no need, for example, to do increment on it. Okay, just keep it the same here. And usually here also with the multiplication and division, sometimes we gain more significant figure, okay, or lose number of significant figures. For example, if you look for this number, the example at the end here that we put it, if we take the division between these two numbers, 65.937 over the second number is 0.46. Okay, these contain 2 significant figures, and these contain 5 significant figure, and the result will be this one. Just to clarify what we have. So with this one, the final answer should be reported as 1.3, 2 significant figure multiplied by 10 power 2. Why? Because 0.46 is contain only 2 significant figure.
Doctor?
Yes.
The first example shouldn't be 4.3 times 10 to the power 2?
Which one?
426.
Yeah, should be approximated. Should be approximated in this form.
Yes.
That means, yeah, should be 4.3, 2 significant figure. Yes. Multiply by 10 of power, for example, 2. Okay, like this example. This is just classification, the notes that we have. This is resources. I told you this is a resource from different, not from the books, just from different websites, and clarify what we have here. Okay, so otherwise we focus here how many. This one, if we have here 4, that means we have 5 decimals. Okay, if we put the number in this case, so we have 4 decimals. But usually, Shabab, if we do multiplication, we may gain some this. It's allowed to gain, to have more. Okay, because sometimes with multiplication we gain more significant figures because we multiply. Okay, so this you will find this in the statement. But usually we represent this by. I try to do this using different softwares, different tools. I represent also identify this as a number of significant figure and others, and I try to get the results in this shape, but it appears in this shape. Okay, I don't know what machines they used. but I don't have a calculator. I don't know what's the calculator will represent the result, how the calculator will represent the results. But I use the softwares, MATLAB, and softwares on the website for learning. I try, they represent the result in this shape, but actually it should be like this. Okay, according to the theory of the significant figures. Should be, but sometimes it is represented dependent on the instruction that you have. If you type, for example, in the code, for example, usually, for example, for my case, for me, I'm familiar with MATLAB. Sometimes in my code, I type at the beginning, I use the long format. So represent the full number that we have. So this will represent the number in 8 decimals. Okay, and 8 decimals or 7 decimals. So in this case, usually the number is appeared a full number without approximation. Okay, so it's represent the full number without approximation, like for example, multiply by 10 to the power 2. And usually these terms, 10 to the power 2, 10 to the power 6, just insignificant numbers. Okay, and the significant number is this number. So in this case, what we have here, this is actually the result should be appeared like this one, but on some machines is appeared like this one. Okay, but from the theory or from the science, if we have good machines, the result should be like this one. For example, if you do calculating, you have result like this one. But with significant figures, the final result should be reported in this form, according to the rules that we have. Okay. If you have calculator, please try this. I don't have. If you have calculator around you, try this division and see what's the result. If it is multiplied by 10 power 2, it is fine. Okay. If it is this number, that means also you ask your calculator to do it correctly again. Okay,
no,
so
it's with decimal basis.
okay. Until here, يا شباب, that's the review that we have it about round off and significant figure. Because why we need this, يا شباب, from you? In the exam, usually, for example, we give you to compute the errors and you compute the value of the error. And the question otherwise write the type or the result, for example, in 3 decimal places, or for example, write your result, for example, 4 decimal places. Write your result in 4 significant figures like this one. So you have to know the definition of this. What we mean by this one. You can get the result, but you have 2 marks or 3 marks on how you do this simplification or how you use this representation in the exam. So in any exam, usually we will have a common result. We should have accurate result. We will force you to do this one. For example, I will give you a table. To fill the table, use, for example, 2 decimal places or 3 decimal places. So all the students will write the same answer if they do the calculation correctly, because we have the same approximation, we have the same problem. So at the end, the results in the table will be the same. Okay, should be the same if you do if you do it correctly, or the procedure will be correctly. Okay, so please, Shabab, review this one. I will give you this, and I want to do this during the class, but I will give you this as homework. You have more time to do like this one. Inshallah, I will send it tomorrow or today. And after that, inshallah, you have plenty of time to review more for the exam. Just review it, and homeworks may also the quiz, inshallah, next week. Okay. I think I inform you that the midterm seems to come at week 4. Okay. We got an official information from that the midterm will be in the week 4. It might be a week 4. Okay. Week 4, around week 4, like this one, at the end of week during the study. So you have classes and exams at the same time. Okay, so you want to prepare. I will submit, inshallah, lecture by lecture. I will try to prepare unit 2. I will submit it early, inshallah, this weekend. So in this case, you can review the material early. Any question until here, Shabab? Okay, because as we know, ya shabab, the problem that different computers and calculators carry out the rounding off in different ways. Okay, so it's not a fix. So they do it in different ways. Okay, so this why we do the rounding, because the hardwares are expensive, and if we minimize the numbers that we represent, that mean we need minimum cost. This will make the system more faster. Yes. Okay. Thank you. Okay, the other things is very important also for us is the accuracy and precision, and we know accuracy is related to how close to the true value we are, and accuracy that this is equal the pies, and accuracy is usually is very important, how your shot is accurate, or how your result is accurate. That mean if this is the true value, يعني how close your shot or your results is close to the true value. While the precision is related how close your measurement. If you do a lot of measurement, how close your measurement. Sometimes we need, for example, for engineering, we need to do here, we need to do calibration. If we have a good precision, that means we do our experiment correctly, because the result with that we get from this experiment are close to each other. That means we do our experiment correctly. So in this case, that means we have an error with the equipment or the hardware. So in this case, we might need some calibration to the equipment. From this figure, you can see we have 4 graphs here. As we go to the right, the accuracy will increase. As we go below to the bottom here, the precision will increase. You can see the first graph. This is the true value. The middle, this will assume this is the true value. You can see the results. Some results are near to the true value or close to the true value, and the majority of them are far from the true value. In this case, this system is inaccurate. The precision is related to how close your estimation to each other. Okay, so here this also imprecision, because all the results are also not close to each other. Okay, so what about B, ya shabab? Figure B.
B is not accurate, not precise.
Neither.
A not accurate. Not
B is
precise.
accurate, but not precision.
Accurate.
Yeah, B is accurate يا شباب. B is accurate but imprecise. Okay, what about C?
Precise but not accurate.
Yes, B is precise but not accurate. Okay, precise يا شباب. Accurate should be near to the true value. The true value is at the center or at the core. If we are near or around the true value, that means we have an accurate result. If your estimation is near to each other, okay, your estimation, for example, in this case, our estimation is close to each other. How close this estimation to each other? We call this precise. Okay, so all the estimation here is close to each other, but this far from the true value, so this will be precise and accurate. Okay, so here this is all we have a distance between, or considerable distance between our estimation, so this will be imprecision, or we have uncertainty here. This one you can see our result is close to the true value, so this will be accurate but imprecise. The last one is clear, all your shot at the center, so in this case your measurement or your result are accurate because we close to the true value, and also precise because all the results or all the estimation are close to each other. Okay, شباب. So So the accuracy is to get all your shot, for example, near, for example, the target. That mean the degree of the perfect. Okay, how the degree of the perfect or the degree of the perfect of the measurement that you obtain. How perfect measurement that you have. Okay, so the precision just to get all the result or the estimation close together. This usually, if we have precision, as we said, usually if your measurement, for example, if you do an experiment and you want to measure uh, uh, approximation or you want to measure distance, if you do the measurement and you find it, for example, uh, 1 centimeter or 10 centimeter, after that you do it, you find it, for example, 9.95, you do it again, you find it 9.98, for example. So all the results are close to other. So, but the true result, for example, it is 12. So in this case, that means you do the experiment correctly. You do the experiment correctly, but the problem now, may you have an error in the device, okay, or you do the correctly the experiment incorrectly, but you do it the same time in the same way on all your trial or your steps that you, okay. So here this is sometimes in the labs, if we have a precision experiment, that mean we do the experiment correctly. Sometimes the device we need to do some calibration. Okay, some calibration. If we are far from the accuracy also here for the accuracy also, because we have some errors in the measurement. So in this case, we need to offset or also calibration here. Sometimes we have some offset. So in this case, by calibrate the sensor, in this case, we can get a good result. This is regarding the accuracy and precision. One of the main parts here in this topic, this will be the error. So all what will study later, inshallah, is dependent on this definition that we have it here. The definition of the error and how we can compute the error. We will study here two types of error, eitherwise the true error or the approximation error. The true error when we have the true value, or if the true value is known. If we know the true value, for example, of our experiment, I know the true value. In this, for example, measurement or the length of this, for example, device should be, for example, 10 centimeter. But during my measurement, I have an error in this one. Okay, so for example, otherwise 9.95, 10.1. So I have different errors. So in this case, I need to measure this error. So usually, ya shabab, as we know, to measure the errors, to avoid the negative value and the positive value, we use absolute value. Because we focus on how far we are from the true value, not about if the error in the above or below. For example, if we have it here, so this value, it might be assume this is the same distance like this one, but this one might we have positive value, but here we have negative value. So in this case, we don't focus what's the sign it is of the error, eitherwise positive or negative, but we want to know how far we are from the true. So in this case, we'll use absolute value of the true error. So what's the definition of the true error? We stated here ET, and this equal the true value, if we know the true value, minus the approximation value. So the estimation value that we have. يعني أول trial, the first trial. Sometimes, ya shabab, as we said, this true value would not give us a good representation, a good meaning about how far we are from, give us information about how far we are from the true value, but what's the percentage of this error? Is this error big, or if this error is small? Okay, or we, for example, we should consider this error, or we sometimes, for example, if the error is 0 or 1, for example, may we ignore this, or this is acceptable because our tolerance, we have some tolerance in our measurement. Sometimes this error, for example, is even it is only 1 millimeter. Sometimes this 1 millimeter is 50% from the measurement. So in this case, this is big error or huge error, or it might affect our design. So the percentage relative error usually will give us a good meaning how to understand how this error might affect our measurement. So absolute true value or absolute true percentage relative error, we use here small segment here. This equal the true value minus the approximation value over the true value multiplied by 100. To put this as percentage from the final result. Let's take this example. Here, this is from the book, yes, from the textbook. Suppose we have a task to measure the length of bridge. Arrive it. If we measure the bridge and we find that the length of this bridge is 9,999 centimeter, and the length of the rivet 9 centimeter. If the true value of the bridge is 100,000 centimeter and the length of the rivet is just or this pin is equal 10 centimeter. So the question here, compute the true error, and we know the true error is equal the true value minus our measurement, or minus the approximation, or minus our estimation. Okay, so in this case I want to subtract and 9,999 from 10,000. Okay, to find the true value. So the true value here, or the true error for the bridge, is equal 10,000 minus this number. This will equal 1 centimeter. Also, the true value in the rivet also is 10 minus 9 from measurement. We measure this, our measurement is 10 centimeter, and the true value is 9 centimeter, and the true value is 10 centimeter, and the error here also will be 1 centimeter. So now we have the same value of the error. The same value. If someone said I have the error is 1 centimeter, but I measure the bridge, and you measure the rivet, and you have also the error is 1 centimeter. So now the error is the same, is 1 centimeter. But this is not give us how far or what's the effect of this 1 centimeter on in the design of this, or in our implementation of the system. Here we'll use the percentage relative error. This will help us to represent how this measurement will affect our design, for example. If we consider the true error percentage relative for the bridge, so this will equal 10,000 minus 9,999 over 10,000, and this will multiply by 100, and this will equal 0.01%. For rivet, we have this is equal 9 minus 10 minus 9 or 100, and this will equal 10%. You will see this now. The 1 centimeter with respect to the bridge is just 0.01%, and with respect to this pin is equal 10%. So in this case, the error here in the small unit here, like for example, the pins, it has a more effect, or it is much greater than if we compare this, the same error 1 centimeter with respect to the bridge, because the bridge has 10 kilo, okay, 10,000 centimeter. Okay, so here usually the true errors, or what we'll study later, the approximation error, would not give us the effect of this error in our design, but we need to do relative or percentage relative error to see how percentage this will affect our design. Okay, so for example here, because the error is too large, sometimes we need to do to correct our measurement or to adjust our job. Okay, while for example the bridge is very small, sometimes we can ignore this error. Okay, it's 1 centimeter, but here we can ignore it. But here 1 centimeter, regarding to a small device, this we should consider this error. Okay.
So it's clear.
Okay. This is another example here. The true value for example, for the pi. Sometimes if we have some approximation, we have also the true value or the exact value. Here, for example, the pi is equal 22/7. While it is, for example, true value, we might represent it in 8 decimal digits. Okay, so if I have the true value, for example, this is the true value of this of the pi. The pi equal this true value that we have. And my, for example, approximation by using, for example, I approximate the result. I take the division, 22/7. I get this result. Okay. So here, for example, when I compute, for example, the errors. Okay, so the error will equal the true value minus the estimation or the approximation will give me this is the value of the error. After that, if I want, for example, to compute the percentage, okay, how far we are from the true value. Okay, so the percentage usually will give us good meaning about this error. So it is 1 centimeter, but without meaning. So if we need meaning about this error, so usually we'll take percentage. So here we'll take the true value will be the correct value or the exact value of the pi minus the approximation that I do over the true value multiplied by 100. So the error here, you can see it is 0.04%. So the error is small, it might be accepted. Okay, the error is small, it's not that huge. 0.04, okay, percent. So this is going to be accepted. So this the true error, we use it only if we have the true value. But sometimes the true value also not available for us. So we do only approximation. So to do this one, if the true value is not known, so in this case we need to use the approximate error. The approximate error or approximate absolute error is equal the current approximation minus the previous approximation, or the present approximation minus the last approximation. Okay, so if you do experiment, you get one result. So this is, for example, in the table, you have the first column, you have the first result, and after that you have the second result. So in this case, we just subtract the current minus the previous one. The same thing is for the percentage, but here we have the present approximation minus the previous approximation over the current approximation multiplied by 100. Okay, sometimes here in our estimations, we don't have the true value. We just do an experiment. For example, you have data from the lab. After that, from this lab, you might estimate the model, and from this model, you might try to get the value of some parameters. For example, you are interested to compute the value of A. For example, in your first trial of collecting the data, you get A equal 10. The second trial, you have 5. So here we have difference from our measurement. So we compute the approximation error. What's the approximation error? Is equal the present result minus the previous result. To have more meaning about this error, the error, because it is magnitude and value, we want to know the meaning of this one, how percentage this error from the true value or from the approximation value. So in this case, we do percentage relative error. Let's take another example here. Using Maclaurin series expansions, and this is a special case from Taylor series. So here, this approximation of the function, we do here approximation if we have the true value or not have the true value. So here, otherwise we do or compute the true error and the relative true error, and also we compute approximation and error or approximation error relative percentage or relative percentage error. Okay, so here, for example, assume we have this Maclaurin series. Okay, and this is one type of Taylor series, as you know, when we have xi equals 0. Okay, xi equals 0 here. So this special case of the Taylor series, but here we have xi equals 0, and you can see this will be the target that you want here. So because here we usually have h equal xi plus 1, that the value that we want to protect or estimate, okay, minus the previous result, okay, or the current result. The current result is xi, and usually this will start from 0. Okay, and the value that we want to protect, this is x, so this is the value of x. Okay, and this is all these functions are multiplied by the derivative. Here, for example, this multiplied by the derivative. Let's type this one. The first derivative, for example, here, f of 0. Okay, this x multiplied by f of 0, first derivative, and this here multiplied by f of 0, and all of them multiplied by f of 0, but the order of the derivative will increase step by step. Here this first derivative, and this is second derivative, and here we have f of 0 third derivative. Okay, here this f third derivative like this one, and here multiplied by f of 0 fourth derivative like this. Okay, f of 0. What's the function f? This is the function f that we have. Okay, this is the function f, and this is multiplied by the derivative. This is the first term, and this will be f of 0 only, and after that, this will be h multiplied by the first derivative of 0, and this will be h squared, and here will be x only, multiplied by the second derivative of 0 over 2 factorial, and this also f of 0, third derivative of f of 0, multiplied by x cubic over 3 factorial, and plus like this one until infinity. This is Maclaurin series, a special case of Taylor series. If we have the true value of this function, for example, here we want to estimate the value when xi plus 1 is equal to 0.5. Okay, the value now xi plus 1 is equal 0.5. So in this case, the true value that we have it is this 1.648721. So the question here, find Maclaurin series with one term. Okay, so here we want to find the Maclaurin series for one term. That means zero order approximation without any derivative. Okay, after that, for example, we add another term, new term, for example, to improve the accuracy. Okay, to improve the accuracy. So here, for example, find the Maclaurin series with one term. That means I need this term only. So what will be the value now? We start with the simplest version with one term. I will get the function e of 0.5 is equal 1 because I use it now only one term. So here I can compute the error. This is my first measurement. Okay, I use only one term from the series or we call this zero order approximation. Okay, so this is my first estimation. After that, if I need to compute the true error, I can't compute the true error because I have the true value and I have the first estimation. Just I do a subtraction between the true value and my estimation. But the approximation error here I cannot compute because I have only one estimation only. From the second step, I can compute the approximation error. Okay, from the first step, I cannot do this one. Yes, one question here. Okay, 1 minute was yes. Okay, not on the class. Okay. Okay, Shabab. So here, this is my first trial, my first step. I use only one term, or we call this zero order approximation. So I find the value of x exponential x equal 1. So in this case, the true error, I can compute it true. This will equal the true value minus, for example, my approximation. After that, I will compute the error. This is the true error. The approximation error, I cannot compute it in the first step because I have only one estimation. Okay, the first step I cannot compute. So to improve the accuracy, usually we add more terms. If we add more terms, so we will have more, we will be near to the exact solution. Okay, if we add more terms, so the error will reduce. Let's see this one. This is the true. So this is the first estimation. If we add another term, okay, if we add another term, the second step, this is the first step. The second step, if I add another term, that means I use two terms now instead of one term. So I have the first one 1 plus 0.5. So this 0.5 because I want to compute or estimate the value at 0.5. So the second value now it is 0.5. I have the first estimation and I have the second estimation. We can put it in table. Okay. So I just substitute HBAP instead of x by 0.5. So this is for two terms, or we call this first order approximation. We use the first derivative only. So here, ya shabab, we compute the errors, for example, for the error here that I have, for example, regarding the approximation error, derivative for approximation error, I have the first estimation or the previous estimation is equal 1. And I have the current estimation is equal 1.5. So now if I want to compute the approximation relative error, so this will be, or this will equal 33.3%. So the error is large. Okay. Also here, if I want, for example, to compute the percentage true error for the second term, okay, for two terms, not for a single term. This is the true that I have it minus the approximation over the true multiplied by 100. So this will equal 9%. How we do this one, ya shabab? Usually we add terms until we reduce the error to a certain level. We try to reduce the error. If we add more terms, so the error will reduce. We add more terms, so the error will reduce. But the question here, when we stop? Okay, so if you want to stop, when we stop or where we stop. So we have here criteria for the stopping of the, or we call this stopping criteria. For example, here in the approximation errors. This is the formula here that we have it, or error as stopping criteria. What we use here, this is usually to use for absolute value, okay, as a stopping criteria. If we want, for example, to stop when the error is less than a certain value. Okay, when the error is less than a certain value. For example, if the error is less than, for example, 0.001, stop. Okay, or 0.005, stop. If the error is greater than this value, do not stop. Okay, do not stop. For example, here, for example, if the error is less than this value, stop the computing. For example, this error now is accepted. If the error, for example, is 9%, no, this error is still big. It's not accepted. I want the error to be 0.05% or below 0.05. So we determine a number of decimal digits that we accept, the number of digits that we need. After that, we use this formula here. We have different formula of determine the stopping criteria. So the stopping error or the approximation stopping error here is equal 0.5 multiplied by 10 power 2 minus n. Okay, n here percent. Okay, percent. So here, for example, if the result, we want, for example, here to ensure that the result is correct at least 3 significant figures. Okay, at least 3 significant figures. So the error, ensure that there is the error or the result is correct to at least 3 significant figures. So here we substitute instead of n by 3. So what will be the value of the error? Okay, so in this case, what we have, I have 0.5 multiplied by 10 power 2 minus 3. So this will be minus 1. Multiplied by 0.5, this will be 0.05. Okay, 0.05. Okay, so the error or the stopping criteria or the approximation error or relative approximation error should be less than this value. Less than or equal this value or less than this value exactly. Okay, so here we do our calculation. We add term by term, add term by term until our approximation error falls below this value. We can see at the beginning, for example, the first step when we add only one term, we don't have approximation. We have only the true value we can compute. The second step, what we do, we just add what we call this more terms. If we add second term, the error will decrease. If we add more terms, the error will decrease until, because if we add more terms, we will be close to the exact solution, because the exact solution of e of x or exponential, the function exponential with this of power x is equal this series until infinity. If we add more terms, that means we are close to the true value. If you take this value enter here, so this value will be the error. So the error will be large. If we take only this value, 1, so these numbers will be the error that we have. If we take more values, for example, enter here, so the error will be from here. So the rest will be the error that we have. That means if we add more errors, more terms, we decrease the value of the error and we will be close to the exact solution. Okay, we'll be close to the exact solution here. Any question يا شباب here?
دكتور
Yes.
انا اللي فهمته انه مثلا اذا جاني خلينا نقول 0.7 او خلينا نقول مثلا 1.7 الرقم اللي اختاره to start with will be 2, right? The closest integer.
Yeah, here for example, x, you mean?
Yes, assume the x is 1.7.
Yeah, 1.7. Yes.
We will go with the approximation that x equal to 2, right?
Why x equal to?
How can we estimate 1.7, for example?
Here, no. This is the Maclaurin series for exponential. I will give you this equation in the exam, okay? This series that you have it. And here in Maclaurin series, you start from 0. For example, you here, x equals 0 at this point. For example, the figure is here. Okay, so x equals 0. And you want to estimate the value, the shape of the figure at 1.7.
Okay.
Okay, so this one, if you want, for example, to find the first term, that means when we use the first term, or we call this zero order. Sometimes we call this zero order derivative or zero order approximation. We don't use any derivative. Zero order. اوكي هذا نسميها زيرو اوردر ابروكسيميشن او نسميها ذا فيرست تيرم وي يوز ات. انت تشوف هنا الفيرست تيرم كم عندك؟ انت تاخذ الفيرست تيرم فقط. الفيرست تيرم از كونستانت از 1.
اوكي.
The first term is 1. The second term you have difference. The second term here will be 1 لو هذا الفيرست term. The second term لو انت عايز تقول add second term نسميه هذا الفيرست اوردر. الترم الثاني هذا نسميه الفيرست اوردر. فيرست اوردر approximation. هذا نسميه الفيرست اوردر approximation. Here انت use هذا الترمين مع بعض. اوكي. These two terms هيصير عندك 1 plus 1.7. الآن في difference. Okay, you have 2.7. Actually, this x, if I increase this one, the second term you have the first derivative here. Because we use in Maclaurin series, xi, you'll see this inshallah when we talk about Taylor series. xi equals 0. Okay, like this one. Multiply by x, x هذا الvalue. Okay, over factorial 1. This is 1. Okay, here this is derivative is the derivative of this function, and we know the derivative of exponential x is equal exponential x. I'm right?
Yes.
After that, x equals 0. تعوض بال x equals 0. Substitute instead of x equals 0. This will equal 1. So that means this is multiplied by 1. All of them multiplied by 1 because all the derivative from first derivative to n derivative, we have the value of the derivative equal 1. So we write the equation in this form. هذا نسميها ماكلارين سيريز. اوكي. هذا الترم وكل ترم تضيف. بعدين في الترم الثالث لو if you want to take the third term هيصير عندك هنا 1.1 هيصير مثلا الثيرد ترم هيصير عندك 1 plus 1.7. If you want to add more, this will be plus 1.7 square now over 2 factorial. The third approximation. Okay.
And
like
the more we add, the more we increase the accuracy of our approximation.
Yes. Because you see, هذا يا شباب هذا correct solution. This one, this we have it. All the values that we have it here is the correct solution that we have. This is the exact solution or the exact representation of the function. If we add more terms, if you take this one, only the first term, so this rest from here to here, this will be the error. Okay, لأن error is equal. The error will equal the exact solution will be e minus 1. Okay, the error, a true error equal what? Let's write this one. True error here. A true error is equal e, the function or the exact solution, represented by e, minus the terms that you use. For example, if you use only one term, so this will be minus 1. That means the error will be from here to infinity. If you use 2 terms, so this will be the error will be e minus x plus 1. Okay, so the error will be from here to infinity like this one. So that means if we increase the terms, we will be close to the exact solution. Okay, so in this case the error will decrease.
ممتاز دكتور. طيب سؤال ثاني إذا تسمح.
الله يحفظك.
How many functions are we going to deal with?
How many functions? What do you mean?
I mean, how many approximation of functions? For example, we have the exponential the approximation of the exponential function here. How many more functions are we going to take?
Different type of functions or
Yes.
different type of terms, you mean?
No, different type of functions.
Yeah, usually we have different type of functions. يعني exam otherwise you have series, you have exponential, you have sine wave, you have cosine wave, like this one. Usually we'll use functions that you can do. Otherwise, for example, if you need functions, you need the derivative. Otherwise I will give you the derivative of the function in the notes, for example, or for example, if you need this one. Okay, for example, if you need the derivative, for example, exponential or sine wave, you forget, or derivative of, because this and the approximation of Taylor series, we need to compute the derivative for each term. The first derivative, second derivative, third derivative, like this one. Okay, so what we want, inshallah, will be available for us, inshallah, in the exam. All the tools, but usually we have otherwise yeah, traditional, or we call this traditional series, sine, cosine, exponential, or in terms of x, like this one. Any question, Yeshua? Any more question?
Doctor, the value of 0.5 in the exponential, how we got 0.5, I mean?
Where?
The value 0.5, which is an exponential.
This one? Yeah, x equals 0.5, you mean? Why?
Yes, how we got it 0.5?
Yeah, the question is to estimate the value of the function when x equal 0.5. This is from the question.
Okay, this will be appear from the question.
Yeah, the question, for example, question we told you start from x equals 0, okay, to x equal 0.5. You know the value of x equals 0, or use x equals 0 to find the value of x equal 0.5. هذا نسميها ماكلارين. If the first term is 0, هذا نسميها Maclaurin series. If this is not 0, for example, this is 1, and this, for example, 1.5, so the first one is not 0, هذا نسميها traditional or the general form of Taylor series. But if the first one is 0, we call this Maclaurin series, the sample way of Taylor series. Okay, so this is just the target. We want to estimate. Someone, what if x equal 0.5? What will be the value? You ask me. What's the value of the function when x equal 0.5? I don't know. I do approximation. Okay, here we do approximation to get the value. Okay, clear, Isha? So if we add more terms, what's the stopping criteria? This one, we add more terms until the errors falls below this level. Okay, so here, for example, we have table of the true value and approximation. Okay, for the same function. Okay, so here, for example, for the first term, we know we use only one term. F of exponential x is equal 1. So the value of the function or the approximation is equal 1. So the relative true error is equal 39.3 at the first. The first one, the first step, I don't have previous estimation, so this will not be applicable. The second step, I do the second estimation, I have 1.5. The true value or the relative true value reduced to 9.02. And here we have the approximation relative error is 3.3. After that, we do approximation. You can see, Shabab, here the results. If we add terms now, we have how many digits are the same. We have until now is 3 digits. Now here we have 4 digits are the same in the results. Okay, so here we have how many digits are the same in the same results. So if the results is acceptable, so after that we compare this criteria. This is stopping criteria. And the stopping criteria, we assume that an approximation error should be less than. Okay, less than the stopping criteria. And the stopping criteria we decided to be 0.05. If we look for this one, all this greater than 0.05 until we reach the last step, term 6. So we fell now below this stopping criteria. Until here we can stop. Okay, the stopping criteria we decided. So this will determine how many steps that we need. Okay, how many steps that we need. Any question يا شباب regarding this one? Clear يا شباب what we do?
Clear.
Yes.
Yeah, we have here, this is criteria, stopping criteria, adding more terms, this will give us better approximation. Add the terms until the absolute value of the approximation errors falls below predefined, for example, error criteria, depending on the number of significant figure that you want. For example, this is the criteria that we use. If we need, for example, 3 significant figure, so the stopping criteria will be this one. This, if you return for this one, this function here that you can see, usually in computing this one Taylor series, what we have the first term. I need a place here, for example. This is the exponential, for example. The first term is 1. The second term is the first derivative with respect to x, the starting point. This is the starting point. Multiply, if this is x2, for example, this is x1. Okay, x1, I will use it x1. Okay, so I have here x2, the new result, minus x1 or x plus I will take the second derivative of x, the initial value that I started from the result that I want, the point, minus x over 2 factorial. So the factorial here, the order of the derivative, I will take the factorial for. After that, I will continue like this one until infinity. How many terms we need is dependent on the question. Sometimes we told you only we need 0 order approximation. That means you use only 1 term. First order approximation, you need first order derivative. That means first order approximation, you need the first derivative or the linear equation until here. Second order derivative, you need the second derivative like this. So we'll take, if you take more terms, this will give us a good result. For Maclaurin series, we have a value of x is 0. هذا x equals 0. We start from 0. Okay, so in this case, this will simplify. This will be 0 and this will be 0. And here I substitute, I will take a derivative, and because here I have exponential, so the derivative of exponential is the same thing, the same function. Because this is positive, so it will be the same. After that, if you substitute instead of 0, all the results will be 1s. Okay, so if you return to this one, you'll find this is not considered because it is equal ones. The first derivative, and after that we take the first derivative. After that we substitute instead of x2 by 0, so x1 by 0. Take the second derivative. After that we substitute instead of x2 1 by 0, like this one. So all the results here are 1s. So it's not appear in Maclaurin series. Also, if we take the derivative here, this should be square. If we take the derivative here, subtracting here, x2 minus x1, also x1 is 0. So I have only x2, and x2 in our equation is 0.5. Okay, 0.5. So this Maclaurin series. Inshallah, in the next class, we'll talk about, we'll take a review to the Taylor series and the special case in Taylor series. The same things. If we understand this example, the rest will be okay. Okay, I think we need only next lecture to have plenty of 3 or 4 examples. After that, inshallah, we'll give you an homework, inshallah, to solve at home. 2 problems or 3 problems and relate to this. This, inshallah, will be enough for the first summer. Okay, you can see here, this is the estimation or the result that we want to protect. And this is the when we substitute instead of S by 0, for example, by initial value. And here we have the first derivative. This will be the distance or the step size, the difference between the initial and the point that we want to protect. We take the second derivative over 2 factorial. And the distance will be squared like this one. We add more terms until we get 0. Here we stated that the Maclaurin series is special case of Taylor series when xi equals 0. Okay, so this way you have it. Please, Shabab, go through the examples. Next class, inshallah, we'll try to review this material to finish this week with this material. We have still different examples to solve. We'll try to cover these examples, inshallah, to finish this topic. Any question, Shabab?
الله يجزاك خير يا دكتور، شكرا. Have a great day.
Okay, thank you.